Okay, so today we're going to start off talking about chemical imaging for cancer pathology. Okay, so the goal of this is going to be to introduce you to mid-infrared spectroscopic imaging, or FTIR, or often used here called infrared spectroscopic imaging, even if they're referring to mid-infrared. So I'm going to talk a little bit about the advances in technology. This is a field which has seen massive advances in technology over a very short period of time. It's almost a new technology actually to what it was even 5-10 years ago. And then I'm going to focus more on the biomedical applications. So what can you use it for? What applications would this be valuable for your future careers for? Okay, so the sort of general goal of our group, certainly on the bio side, is looking at molecular and structural analysis. So if you're interested in molecular and structural analysis, the conventional way to do this is use staining. This can be spatial staining or immunohistochemical staining. Okay, exam's late. Okay, so what we're developing is an alternative to this, which is called chemical imaging. So this in general includes FTIR and also things like Raman spectroscopy, near-infrared. So Matt Shumerick spoke to you all last Thursday about Raman spectroscopy. So FTIR is a complementary technology. It's much faster than Raman and is much more amenable to imaging. Okay, so I want to start off, I'm going to split the talk into two parts. The first I'm going to talk just very quickly about the background to FTIR, a little bit about the instrumentation, just to kind of give you a feel for that side of things. The second part of the talk, I'm going to do the more interesting stuff, which is the biomedical applications. So some of the work that we've been doing in our group and the work that I've been doing over the last few years. So Zam and Grace will have shown you last week or earlier this week some of the FTIRs. So I've spoken to you a little bit about the instrumentation, but we'll delve a little deeper. Okay, so as Matt spoke to you last week, just to refresh the slide, FTIR is a type of spectroscopy. The goal of spectroscopy is to input known radiation and detect the exiting radiation, and this will tell you something about your sample. Okay, so with FTIR, we are particularly interested in this region here, the mid-infrared of the electromagnetic spectrum. So the infrared is divided into three areas. You have far infrared, mid-infrared, and near-infrared. And different regions of the infrared will give you different information. So you can use things like rotational spectroscopy. You can detect overtones and harmonics in the near-infrared. But in the mid-infrared, we're detecting fundamental vibrations of chemical bonds. So the basis of FTIR, or infrared spectroscopy I should say, is that there are specific frequencies in the mid-infrared which are resonant with certain chemical bonds. And the frequency is different depending on the chemical bond. And this is basically determined by the shape of the molecular bond, energy levels, and mass of the atoms. So in general, what mid-infrared can do is give you a measure of most covalent bonds, as long as they are electronegatively different. So typically things like CH, COO, NH are very IR active and will give you a high absorbance. So in general, you can divide chemical bonds into those which are IR active, where there is an electric dipole moment change, and those which are IR inactive. In general, a general rule of thumb is that if something is IR active, it tends to be poorly active in the Raman and vice versa. So they tend to be fairly complementary in that respect. Okay, so why are we interested in this for bio applications? So the basis of what I do is to use mid-infrared to probe the biomolecular structure or biomolecular components of cells or tissue. And essentially what we can do is, by measuring the chemical bonds and measuring the absorbance, it gives us an indirect measure of things like proteins, lipids, DNA, glycoproteins, phosphate, collagen, extracellular matrix type proteins. And from this we can derive an absorbance spectrum. So this is just a small portion of what we can detect. So you'll see something similar last week. In fact, I think you all took images of this last week. So essentially these different peaks correspond to different fundamental vibrations. So you can do things like, in fact, actually with mid-infrared, you tend to get peaks like this, which are composed of multiple peaks. So, for example, this is CH and NH, and you can do spectral deconvolution if you're interested to sort of parse out the different components. So, different chemical bonds will have different modes of vibration. So this is this is stolen from Wikipedia. Things like the CH bond will have different modes, and this is probably the most common. And the different vibrational modes will correspond to different frequencies. So what you can do actually is you will get 6 discrete peaks from the same CH bond in different regions just by how it's vibrating. An important part about this is that from a bio perspective, this is really important. So what you find is the different chemical bonds will vibrate in different modes depending on what structure they're in. So for example, lipids will have a different vibrational mode to proteins in general. So what's an FTIR look like? This is a really horrible drawing I did when I was a PhD, and I haven't changed it yet. So last week you will have seen our FTIR instrumentation downstairs. It's basically broken down into 2 components. You have the bench and you have the microscope. This is the bench. It's actually fairly simple. We have an infrared source. This is a broadband mid-infrared source. I'll talk about these a little bit more in a moment. We then have a Michelson interferometer, which I'll speak about, a chamber where we can put our samples, and then a detector. I'll speak a lot more about these in a moment. What we can also do is couple this to a microscope. So you'll have seen this last week where you were imaging mouse brain, rat brain, I think it was. And I'll show you an example in a moment. Okay, so this is the boring part. So infrared was discovered in 1801 by William Herschel. He noted there was an increase in temperature past the red part of the visible spectrum. And it was later on that this then started to be used for spectroscopic studies. So there's generally 2 types of spectrometer. There is a dispersive spectrometer, which is a monochromatic source of infrared. And you can vary this. You can basically scan across the frequencies of the infrared. This can be done with a prism or later advances in grating. This has been largely replaced. Actually, in truth, it's coming back in. There are advantages to this. So this is, interestingly, actually coming back into fashion, which is new. But it's been largely replaced by Fourier transform, FTIR, and the big benefit of this is you can scan much faster. You're not having to scan a wavelength at a time. You can do all of this once with a single sweep of the interferometer. So, as I said, the main source is this Globar mid-infrared source, which you have in your desk, in your benchtop. There are 2 types, Globar and Nernst. Essentially what this is a heated wire. You heat it very high, emits infrared. This is actually fairly dim. It's still a lot brighter than something like the sort of older monochromatic sources, but it's still relatively dim. This has been an area of a lot of focus. So actually the signal to noise is really high with mid-infrared compared to something like Raman. But it's still quite dim when you're doing diffraction limited measurements. I'll talk a lot about that later. But there's been a lot of work actually on improving these sources, getting brighter sources so you can get high resolution measurements. This you can do using a synchrotron, I'll talk about in a moment. Or what I haven't actually put on today is there's been a lot of work on quantum cascade lasers, which are actually need to be scanned, but can get a very, very bright source of infrared. And they're just coming onto the market now. Okay, so many of you will be familiar with interferometry. This is the FT part. So essentially, the infrared comes into your interferometer. It's split by 50-50 by a beam splitter. 50% is reflected to a stationary mirror, 50% to a moving mirror. This mirror moves, so it creates a path difference. It then reflects, recombines. 50% is destructed, and then 50% is modulated and goes into the bench. So I'm not going to talk too much about FT. I'm sure you're all familiar with that. Okay, so the next part is the infrared goes into the chamber. Something very exciting here. If you're looking at just a homogeneous sample that you just want to take a bulk measurement of, you just put this in your bench, take spectrum. One of the new things which has sort of emerged over the last 10 years is coupling these with fully functional microscopes. So you can pick areas, and you'll seen this last week, do imaging. Okay, so this is what you will have seen last week. This is the bench. The source is back here in the system. The interferometer is down here. This is the chamber, and the detector's here. And this is the microscope. So you can basically bypass the chamber and go straight into the microscope. And we'll talk about that in a moment. Okay, so the single biggest advance in FTIR spectroscopy has been in the detectors. I started my PhD in 2005, and then came here in 2008 as a postdoc. I was working with single element detectors all my PhD. So you'll see the speed increases have been massive over a very short period of time. So there's basically two types, or really three types of detector. There is a single element detector, which is just a single detector. It's very cheap. It's great for bulk measurements. If you're interested in looking at polymers or even cells in culture, it works very well. The advances have been on the multi-point detectors. You can get linear array detectors, typically in configurations of about 16 bits. And now there are these focal plane array detectors, which I'll show you in a moment. So last week, actually, you were working on the Spotlight, which is a linear array. The one next to it, the big one, was a focal plane array. These were actually originally developed by the military for weapons guidance for missiles. They declassified those in, I think it was early 2000, and now they're relatively widely available. Certainly in the US, they're widely available. It's a little bit more tricky in Europe, and certainly in Asia. Okay, so the big advantage with these is they're obviously much, much larger. A single point detector you can actually image. It's actually not called imaging, it's called mapping. It's just one of these things spectroscopists came up with. And essentially you sequentially take single point measurements. It's very, very slow. I spent many, many hours doing this. The linear array, which you did with Zam and Grace, basically raster scans across your sample, swoops across and collects an image. And then the focal plane array, you can just take large images. This is just like a CCD digital camera. Typical configurations for this are 64 by 64 or 128 by 128. So you can see this tremendous increase in number of detectors. So the speed has become obviously much, much faster. The big benefit with this is, from a biological perspective, is we just couldn't image tissue fast enough in the olden days. Now we're sort of on a clinically feasible scale. So a lot of my work, and I'll talk to you in the second part of this, is for clinical translation of these technologies. In fact, imaging is even quicker than the detector. The increase in detector will give you reason to believe. I will talk about that maybe a little later in some of the other images. But basically, I'll talk about it now. So with a single point detector, you define your spatial resolution, so the area that you're sampling, by using infrared opaque apertures, so basically above and below your sample, or to the side of sampling. This cuts out a huge amount of infrared. You get very little throughput. With imaging, it's actually focused to a point using Cassegrains. I'll show you that in a little bit. And we're not using infrared opaque apertures, so you actually get a much higher throughput of infrared. So you can actually get a couple of speed improvements just from getting rid of these apertures. Okay, one thing I just wanted to mention at this point is you can also do ATR, FTIR. This is really cool. It's actually one of my favorite applications, or one of my favorite add-ons. The idea with ATR is you actually use a internal reflective element, typically diamond or zinc selenide, germanium. The idea with this is that this is a crystal with a high refractive index. So it actually gives you two benefits. One is you can do a high spatial resolution. I'll show you some bio applications later. And also you tend to get reduced artifacts from scattering. I'm not going to talk about scattering today. The principle with this is that the infrared goes in. This is actually two slightly different modes, but the infrared goes in. It undergoes total internal reflection. So this is from the source. This goes back up to the detector. And essentially what happens is you create an evanescent wave at the surface of this crystal. And you bring this into contact with your sample, and you can get a spectrum. This is one of the imaging ones in the lab downstairs. Okay, so as I said, I want to just flip back to the source aspect. So the sources have been relatively dim. And certainly if you're doing point spectroscopy, where, as I said, you have these infrared opaque apertures, it's very difficult to get light through when you're looking at the sort of diffraction limit. So if you're looking at sort of 2 to 10 microns, using these infrared opaque apertures, it's very difficult to get enough IR through there. So one of the things that you can do, and this was very popular, is to use a synchrotron. So I don't know how many are familiar with synchrotrons. There's one in Chicago at Oregon. This is one that I used to go to in France, in Grenoble. There was one in England, in Daresbury. There's quite a few around the world. We also go to one up in Madison, Wisconsin. Oregon actually doesn't have infrared capabilities there. They have, I think, the most powerful synchrotron in the Western Hemisphere, so they typically stick with the X-rays, which is, they need a higher energy. So the principle with FTIR is when you're looking at sort of diffraction, synchrotron, is it's a much brighter source. Certainly when you get to the diffraction limit, you can get a very, very high flux. Just very briefly, the idea with synchrotron is you have an electron gun. You shoot into a booster ring where it starts to spin. You then dump this into the storage ring where electric field and magnets bend this. And as these electrons are bending, they emit broadband electromagnetic radiation. So you can do pretty much everything from X-ray down to microwaves. X-rays are very, very popular. X-ray crystallography is very common on these. And you can filter out mid-infrared. So it's a very, very bright source of mid-infrared. One thing I'll just very briefly touch on now is this has been widely used for point spectroscopy, as I said, with the apertures. The advantage of these tends not to be as great when you're spreading the beam. And up until very recently, and we actually published it in Nature Methods last year, I'll show you some data from, these have not been coupled to multi-element detectors. And actually the first one in the world was up in Madison with some of our collaborators. Okay, so just very briefly, in general, you can measure, actually I should have included a third slide, you can measure in transmission mode, you need an infrared transparent substrate, reflection mode or transflection, or ATR mode. Okay, now, so I've spoke about the advances in sources, the advances in detectors. Another really important part of this really applies for a lot of spectroscopic techniques, has been the data analysis. So back in the sort of 90s, most of the work was based on just comparing spectra. And as you'll see later, the difference between spectra, certainly from a biological perspective, tend to be very small. So univariate analysis was generally insufficient for sort of identifying these very subtle changes. So univariate, I mean just comparing graphs. You know, it's not like mass spec where you have these very significant differences. So the emergence of multivariate analysis and classification has really driven this forward, this field forward massively. So in general, there are two types of classification that spectroscopists will use. One is an unsupervised approach. This typically is things like principal component analysis, PLS, very useful for discovery. Artificial neural networks, technically, depending on what mode would fall into this. Or you can use a supervised approach. So this is where you have prior information and you'll be able to classify it. So I'll show you some Bayesian stuff later, which is a supervised approach. Okay, lots and lots of different types of approach. Everyone has their favorite. PCA is very useful. Linear discriminant analysis is very useful. Bayesian. Okay, this is the exciting part now. So I want to go on to talk more about the sort of applications and get away from the sort of instrumentation side of things. So one of the main things that our group has done, and again this has been driven a lot by the advancing technology, is to work in imaging. So this is the actual microscope. So pretty much everything we do in the lab works with the microscope. We just use the bench as a source of IR. This is a visible microscope and an infrared microscope. Just flip a mirror and you can do both modes. So I want to talk first about the single point mapping and then show you the sort of advances and give you a sort of history of IR and how it's sort of led a lot of the bio applications, certainly from my perspective. Okay, so regardless of what type of detector you use, the end result is the same. And this is something that I just want to make sure everyone's clear on. When you do infrared imaging, you end up with a data cube. So you have your X and Y dimension, which is your spatial dimension, and then you have your Z dimension, which is your spectral dimension. So this is just the same as a visible image. However, instead of red, green, and blue in your Z channel, you'll have all this chemical information. So you'll have thousands of absorbance bands. So the principle is each pixel within this image will have the whole absorbance spectrum. Yep. Okay, so I talked about point detectors earlier. These are still very useful. If you're looking at something which is homogeneous, something where you don't need structural information, just chemical information, so particularly cell biology, this is very useful. So for example, part of the work I used to do as part of my PhD was looking at chemical changes associated with premalignant cervical cancer, and we showed that we could see chemical differences which were unique to low-grade, high-grade, and invasive carcinoma. One of the things we've been working on in this group is looking at cancer development, particularly stromal involvement in cancer development, and things like toxicology. This is potentially a very useful tool for tracking holistic chemical changes with whatever you're interested in, toxicology or cancer development or anything which you're using 2D cell culture. Okay, so what I want to talk about now is one of the big projects of my PhD, which was stem cell tracking in the gastrointestinal tract. So adult stem cells are the source of new cells, so these are responsible for tissue regeneration. So one of the most interesting tissues actually is in the GI tract, particularly the colon and the small intestine. And this is the most regenerative tissue. And the stem cells, so you have, this is basically the lumen, and these are crypts. So your whole GI tract is comprised of crypts. In the small intestines, you'll have these additional appendages, which are called villi. So basically, in the colon, the stem cells reside at the very base of the crypt. These then differentiate into transient-amplifying cells, and then they move up into differentiated cells with 4 different cell types, and then eventually they'll slough off into the lumen. In the small intestine, the stem cells reside a little bit higher, about positions 3 to 5, and you have a couple of other cell types, CBC cells, Paneth cells, and basically what happens is the stem cells differentiate downwards and upwards. One of the big difficulties, and a lot of this work was driven with, I think Queen Mary's in London, was the lack of intestinal stem cell markers, and actually lack of adult stem cells. Adult stem cells are very, very difficult to identify, certainly using conventional stains. So we want to see, do stem cells and transient-amplifying cells, do they have a unique biochemistry which is which can basically segment it out from the surrounding differentiated cells? So this worked really, really well. We did a few different approaches, standard FTIR spectroscopy, synchrotron FTIR in Warrington, England, and Daresbury, Grenoble, France. We also did a near-field photothermal work, which I'm not going to talk about today. And essentially what we could show is when we looked at the crypts, is this is a principal components analysis plot. Are people familiar with PCA? Okay. So the principle with PCA is that you take every spectrum and you look for the variance. It basically finds the eigenvalues, and each spectrum becomes a single point. So you can plot it on principal components. For example, principal component 1, principal component 2. This is the PCA scores plot. So basically the basis behind PCA scores plots are that closeness on a scores plot is related to spectral similarity. So the further apart, the greater the spectral similarity, therefore the greater the biochemical dissimilarity. So what we're looking for is clustering, which implies there is a chemical similarity. So you have stem cells, TA cells, and differentiated cells. Okay, so this worked really well. We could do this across tissues, and we found a very unique marker of stem cells, TA cells, and differentiated cells. Now the next step was to see, could we do mapping? Could we actually find markers and images which basically flag stem cells? So we found a number of these. This is colon, I think these are both colon, yes. We could map this even at very low resolution. One of the markers we found was symmetric phosphate. So this is associated with DNA conformation. What you found is that there was an increased absorbance at 1080 at the base of the crypts, which corresponded with the stem cell location. What was nice is we could even do this on small intestinal crypts, and these markers translated very well actually over into small intestine. So if you remember, the small intestinal stem cells are a little bit higher up in the crypts, and you can see here that the markers flag in the stem cell location. We actually followed this up with a further paper in Stem Cell Research in 2009. This is actually a fairly complex system. Colon's fairly simple. The small intestinal crypts are, there's actually a number of stem cells, or stem TA cells. So if you're interested in that, check that out. It's really quite interesting. But essentially the take-home message was that the stem cells across the GI tract were very repeatable to mark, chemically unique, and also were very similar even across tissues, even though they're in different locations and are subject to different stem cell niches. Okay, so as I said earlier in the talk, this was back at the end of my PhD, which was really very sort of old technology compared to what there is now. And since then, there's been a huge increase in speed, spatial resolution, which I'll talk about in a moment, and the computational approaches. Okay, so how are we doing for time? Okay, so as I said, we have had these big increases in detectors. We can now image faster. So I moved here in August 2008. And one of the things I was interested in is using infrared imaging for cancer diagnosis, particularly for improving cancer diagnosis and prognosis. So a lot of my work has been driven. So I work with Call Hospital, which is just over the road, and with the Department of Pathology in University of Illinois, Chicago. So a lot of this work has been driven very closely with the medical profession and figuring out where are the needs, where is there deficits in the current diagnosis, and where is there desirable additional information for prognosis. So if you are suspected of having a cancer in particular, or even sarcoma, in a solid tissue, you'll typically go in for a biopsy. So the first step is to take a stain, primarily a H&E. Many of you will be familiar with this. In fact, I think you did this last week. You did some staining of brain. And then you'll have an experienced pathologist will look at this and make a diagnosis, or make a preliminary diagnosis. Off the back of this original diagnosis, you will do additional stains, depending on the tumor. So this is an example. Typically the range of stains that you'll do with breast cancer, which I do a lot of work on. These in the middle are for specific cell types, so cytokeratin for epithelial cells, vimentin for fibroblasts, that's made for myofibroblasts. And then further on the outside, you may do additional prognostic markers. So many of you will have heard of ER, PR, and HER2/neu. And this is really important for guiding treatment of breast cancer. What type of hormonal treatment do you want to use? Okay, so this is very expensive, very time-consuming, and requires multiple sections. These are 3, 6, 7, 8, 9, 10, 11, 12, 13 different sections. The goal of our work is to be able to acquire the same information in an entirely label-free approach using mid-infrared spectroscopy. So we can look at things like collagen distribution based on the images and protein distribution, and then use classification. Okay, so one of the big things that our group's been working on has been building these classifiers to segment out tissue. So in my opinion, the most important part of, if you're doing spectroscopy of tissues, and there's been a big failing actually in the field, has been, if you're just taking bulk measurements of different tissue types, you're going to get cell-specific differences. So a lot of the early work looking at cancer versus no cancer, actually all they're detecting is cell type differences. It's not really cancer differences. So the most important part, if you're doing whole tissue imaging and a spectroscopic approach, is to segment out the tissue first. So, as I said, our work is completely compatible with the current clinical workflow. We take unstained biopsy samples, typically from Chicago or Call. We'll then do staining, we'll do all our immunohistochemical stains, and then we work very closely with pathologists who will give us information. It can be on cell types or grades or whatever it is we're interested in. Alongside this, we'll do our spectroscopic imaging. We'll get our data cube, and then we will do some sort of computation. So, for example, cell type segmentation. So one of the things I want to talk about today is some of the work that I've been doing, which is to segment out breast tissue into its key components. So 8 of the major components of breast tissue are epithelial cells. These, I don't know what people's bio background is, but epithelial cells are the functional cells and the source of carcinomas. Then you have a whole host of stromal components. So you have the epithelial cells, which are the functional components of tissue, and then the stromal components, which are the in the connective tissue. They tend to be the supporting structure. A lot of work is focused on the epithelial cells. These are where the cancer originates from, so a lot of work focusing on this. However, the stroma is very, very important, and diagnostically and prognostically can be very, very valuable. Oh yeah, we'll talk about that. Okay, so you basically have collagen, fibroblasts. These are cells which produce collagen. Myofibroblasts, these are fibroblasts which in the vicinity of cancer will activate and they actually promote tumor invasion. Blood necrosis, this is cells which are dying or dead. Lymphocytes, these are inflammatory cells. And sometimes mucin in some types of cancers. So what I did was take my IR image, and then we took multiple stains and basically segmented these out. So the way we do this, let me just check what my next slide is. Okay, so the way we do this is we'll go through working with pathologists and mark out pure pixels. So we'll say, okay, we'll take a training set and say, these are epithelial cells, these pixels correspond to epithelial cells, these cells will correspond to fibroblasts. We do this for all the different cell types. So this was over 100 patients. Actually, this is a slightly older study. We have 200 patients now. And we will typically mark up about 500,000 to 1 million pure pixels. From this, we then derive an average spectrum from all the different components. As I said earlier, the difference actually with mid-infrared and even Raman is very, very, very small. So you can imagine why, as I said earlier, the sort of univariate type of analysis really is very useless for this type of work. It's for the clinician, it's useless, and for more complex systems, it just falls down. So essentially what we do is we go through and we look for putative spectral features. So these can be absorbance increases, they can be peak shifts, they can be area shifts. So a nice example here is mucin in orange. You can see this is dramatically different. This is glycoprotein mucin, and we get these massive increases. So, for example, if you did a ratio of this peak to this peak, that would probably be predictive of mucin. So we typically go through, come up with as many potential markers as possible. Then what we do is we run our classifier and we do a number of sorting steps to figure out what are the metrics which really give us the best classification, what gives us the highest accuracy when we run our classifier. In this case it was 33. I've actually knocked this down to about 18 now. Okay, so this works really well. When you run this on a training, when you rerun on the training set, you can see you get a very high accuracy of 0.92 area under the ROC curve. This is actually very high. If you look at things like just epithelial stromal segmentation and visible images, you're typically looking around this range. And we get slightly above this with many, many different cell types. You can run this on a validation array, and again, we get a very high AUC of 0.89. It's comprised of multiple cell types and multiple disease states as well. It's not just normal. So it's pretty robust even to things like cancer development, epithelial heterogeneity, and such. Okay, so essentially the take-home message from this is that we're Yep.
Can you just explain training sets for about the different system that you create, or at least specific system with an ability to different?
The training set, sorry, say that again. Yes, it's actually across multiple systems.
Okay, if you just move into different systems,
No. Across, so a good example actually is Rohit Bhargava was going to give this built prostate classifier at NIH, and I've used it on many instruments, and it works very, very well. Yeah. Across detectors is interesting. We've done sort of preliminary studies and we don't see any big differences, but I'm sure he's going to do it at some point. Certainly across the same system, no. Across systems, not really.
Have you tried also different
Yes, we've done a lot of artificial neural network work. We've done some HCA work. I've done LDA work back in Lancaster. Yes, Bayesian tends to be very robust. So the big benefit with Bayesian is over something like a PCA-based approach. Any type of data reduction which is not supervised from the sort of data compression aspect tends to be problematic with spectroscopy. So the big benefit with Bayesian, I just jump back a slide, is because you're picking the metrics, you know that they're biologically real. PCA, or even PLS, tends to err on the side of noise or artifacts. That's not always true, but certainly with spectroscopy is an issue. When you have something like this, because it's true biological peaks, typically when you try on different systems, or if something's gone wrong with your sample, someone sneezed on your sample or something, it tends to hold up very well. PCA tends to fail on these type of things. So yeah. 33 features, yeah. So actually, this has been refined further. I'm just finishing off the validation. I've got down to about, I think down to 18 now. Not yet. We're actually working on that with a visualization postdoc who's down the corridor. But yeah, we're basically, we're talking about doing like a random forest type approach. Yep. Yes, yeah, that's the next step. We're going to be doing that over summer actually. It'll be much faster. Yep. Yes. Yep. Cool, thanks. Okay. So the take-home message from this is instead of needing to take multiple stains, so in this biopsy here, you would need 5 different stains, 2 special, 3 immunohistochemical. Anyone who's done IHC staining will tell you along with text. We can get all that from a single image. So we basically scan our tissue, run our classifier, and it will color code all the different pixels correctly. Before I jump on, this can be really, really useful. Actually, this forms the foundation for a lot of the future work. If you're interested in looking at changes in epithelial cells as cancer progresses, or proliferative capacity, or stromal changes, this is a really important first step because you need to be able to segment out your tissue accurately. So that's my... this is the infrared image. Yes, this is the classified infrared image.
So processed image.
Yes, that one. Yeah.
So it's HCA map or it's...
Oh, this is Bayesian. Yes. So the Bayesian basically predicts, it'll derive these metrics, and then it will give you values, and it will predict what pixel what class a pixel belongs to. Yep, and color code. Yes. No, we've done some work. So you can do a sort of basic cancer classifier, basically using image analysis. We haven't done a tremendous amount on that yet. So there's been a couple of issues. One has been the spatial resolution. This typically isn't great for, I'll talk about that in a moment, the spatial resolution improvement. But yeah, we've done like cancer classifiers. We have a grad student working on, he does a lot more of the image processing side, image segment, image analysis. Yeah, there's a lot of information to derive from this, which isn't used yet. Yeah. Okay. So there's one thing I missed out when I gave you the 8 classes. That doesn't include all the important components of breast tissue. One of the major limitations has been the spatial resolution. So commercial instruments, to ensure a high signal to noise, are limited to about 6.25 by 6.25. The machine you used last week was about this. No, it was 6.25. So this is perfectly fine for the components I showed you earlier. They typically, the cells are large, or they're in components which are large. One of the issues is there are certainly cell types and tissue components which are smaller than this limit and are very, very important. Particularly in breast tissue, endothelial cells, myoepithelial cells. These are cells which line blood vessels. Myoepithelial cells, these are really important. These are basically they segment out they divide the epithelial cells which are here, the functional cells, and the surrounding fibroblasts. This is really important. If you have a benign or something like a ductal carcinoma in situ, these cells will still be here. If it's an invasive carcinoma, these cells will be absent. This is one of the most important steps actually in breast cancer diagnosis. This, from a spectroscopic point of view, is actually quite difficult, certainly with infrared, because the cells typically are on the order of about 4 or 5 microns. But if you have epithelial proliferation in the gland here, they typically squish them down to about 2 or 3 microns. So that's the problem. Plus, they're at an interface of epithelial and stromal cells, so they tend to, with the size of the pixels, get components from epithelial and stroma, and you end up not getting good classification. Oh, and intralobular stroma. So these are, let me just tell you a little bit. I'm just a little, okay. These dark purple blobs, if you will, these are ducts and lobules. These are the functional units in breast. And then the sort of lighter pink is the stroma. So this is typically fibroblast, myofibroblasts. These ducts and lobules are infiltrated with intralobular stroma. This was a big problem actually when you're doing cancer classification, because this can look like a big tumor if you don't have an accurate resolution. So being able to visualize this is important. I'll show you some examples in a moment. Okay, so part of my postdoc has been looking into and advancing a lot of the high resolution work. As I mentioned earlier, you can use ATR, so ATR with a high refractive index. With the Rayleigh criterion, you can actually get about a quarter of a wavelength as opposed to half in transmission mode. This is a contact approach, so let me tell you about this now. So the infrared comes down and it's focused down to a point. This is a 15x 0.5 Na category. This is the crystal. This improvement, this is actually very recent. The availability of imaging ATR elements is quite new. This has given us significant improvements in resolution. You can see things like endothelial cells now become much better to visualize, and now you can extract chemistry from these as well, which is really important for classification. As I said, my epithelial cells, these cells which line glands, we can visualize these and classify these. I shouldn't say classify, we haven't done that yet actually, but we can certainly chemically characterize them. So the improvements in spatial resolution are really important. So this is an example of a TDL you were speaking about before with infiltrating stroma. This is our low res, this is our higher resolution ATR. When we extract chemistry from these, or spectra from these, if you compare epithelial in green to stroma in purple, or magenta, when you have the high resolution, you get a much greater chemical contrast. And this is important because it's this chemical contrast that we use to drive our classifiers. So you can see now that when we're doing things like, if you're using a sort of cancer classifier, you can now see that you can segment out the intralobular stroma from the epithelial cells. So this is really important. So what we're working on now, or Sri is working on now, is developing a high resolution classifier which can now take these new cell types into account. Okay, so one of the things I mentioned earlier is that you can use synchrotrons as a really bright source of mid-infrared And last year, or 2 years ago, I think it was, this was coupled to a focal plane array. This was the first one in the world. So what they did actually in Madison, just outside of Madison, so this is the edge of a synchrotron. What they did is they pulled off 12 infrared beams. Nowhere in the world could you do this. Nowhere in the world would they let you have 12 beams off a synchrotron for infrared, but they managed to do this. They took 12 beams off and combined into one giant beam. And because this is so bright, you can actually funnel it through a 74x 0.65 NA objective, which you can do a glow bar source, or it wasn't bleed up to then, you can do a glow bar source without basically getting no light through. What it's allowed us to do is oversample, so we could get a pixel size on this system of 0.56 by 0.56 microns. What this allows us to do is to oversample, so you are wavelength dependent, so between 1 and 5 microns for the bio range, you're oversampling past this, and this allows you to do things like spatial deconvolution as well, because you're oversampling, which we're just about to submit a paper on. Okay. Oh, I forgot about that. So, just to kind of give you a timeline of the spatial improvements, this is what I was doing for my PhD on stem cell crypts and cervical smears. The advances in detectors, we've been able to improve this slightly, and this is now the type of resolution that we can get using a 74x coupled with a synchrotron. We get much higher resolution images. You can see we've now got access to a lot more structural information, and can now extract chemistry from cell types which were just unavailable with older versions. Published in the Nature Methods, pretty pictures. Need to be a little careful with time. And basically allows you to extract things like endothelial cells, microthelial cells, lymphocytes. Okay, so this was all good and well, but as I said, a lot of my work's been driven towards clinical translation of these technologies. And we're not going to have a synchrotron outside the back of every hospital. So we actually had one of our grad students, Rohit, work on the theory. He does a lot of modeling of, actually this is the first time anyone's done this, is modeling of infrared microscopes. And basically we could adapt one of our existing instruments, this is the one that was next to the one you worked on last week, to be able to do this same type of imaging using a glow bar source. And we just got this accepted. The nice thing is it's readily available, it's low cost. There's actually less image artifacts. Something I didn't talk about with synchrotron is you have 12 coherent beams which tend to interfere. There are ways to get it around that, but it's certainly a problem. The trade-off is we get much lower signal to noise though. What's nice, we can now do this high resolution imaging in our lab. From my perspective, when I was doing the crypts, this is a dramatic improvement. And this is really the sort of state of the art now. And in fact, the next generation of FTIRs that are going to be available will now be using our setup. Okay, good. So as I said, we're sort of working on more comprehensive classifiers. Okay, so I'll finish on that. If you're interested in further reading, I've sort of done a whistle-stop tour today. I think the Nanobiophtonics book's the course book. It's now available on the Kindle, so you have to get it. Kindle. I've got a chapter in there. It goes into a lot more detail about the detectors and the stuff. I also just wanted to say I've had a more recent paper published in IEEE quantum, just like Journal Selected Topics in Quantum Electronics. And it talks a lot more about the high resolution work, the classifier. It also talks a lot about the theory as well. We've done a lot of advances in understanding scattering and stuff like this. So drop me an email if you would like me to send this to you. Cool. Thank you. Any questions?
What sample area you can scan using ATR?
With ATR, it's 500 by 500 microns. Typically, only 400 by 400 that is useful. You tend to get, as you get towards the edge of the crystal, you tend to get a bit like edge effects. Not edge effects, that's not the right word. Basic crystal artifacts. There is now a new 1mm by 1mm ATR crystal on the market. That came out a few weeks ago. I haven't tried that though yet. Imaging mode. You can actually do both. So imaging mode is typically used. ATR mode, for point mode, you do use maybe a diamond crystal. that's actually a lot of the structural work was done on.
One more question. The spectacle. So when you set up sample is exposed to airflow, why don't you use some kind of sample, just theoretically some kind of sample?
Yeah, so actually the machines themselves are purged. In fact, most of our machines are purged with dry nitrogen. Typically, if you're imaging for an hour or so, the atmospheric correction, you'll take a absorbance background and then scan your sample, and that'll correct primarily. There's also a couple of correction algorithms. For anything where you're scanning for long periods of time, yes, it's better in a sort of enclosed atmosphere. So we have an FTIR over at the hospital at Mills, and that's fully enclosed. But yeah, it's okay. It's typically okay if you don't get too much atmospheric change within a few hours, but even a month. Yep. So we use most of it is done using IDL plus NV. I don't know if you've heard of this. It is awesome. Yeah, ENVI plus IDL. It's really, really, really nice. It's the big benefit over. It's expensive, but the big benefit over MATLAB. These images are huge. Shri acquired the 74x, a whole tissue array of 74x, and was it 400 gigabytes? So MATLAB tends to be very poor at sort of dealing with images that large. NV, it's actually NV was built for image analysis of not like satellite data, geosatellite data. It does a very, very good streaming off the hard drive. Yeah, we use most of the scattering stuff, baselining, normalizing, we'll do in NV. A little bit we'll do on the PerkinElmer software, like atmospheric correction. We do have a lot of MATLAB code as well. So yeah.
Can you tell us about the pre-processing when you do the samples? How, for example, the region that you select, what method do you use?
The pre-processing for the samples, so for the tissue work, it's formalin fixed, paraffin embedded, so it's just typical from the clinic. This is section 2, 4 or 5 microns, and we deparaffinize. So we normally deparaffinize using hexane for 24 to 48 hours. You can use xylene. So for example, if you're doing HD, you'll use xylene. It tends to be a little harsh for spectroscopic analysis, so we tend to use hexane, but there is a time trade-off with that. Sorry, what was the second part of the question?
It's when you select your region of the spectrum and then use it in your model, how do you do that?
It's really just, so there's a few ways of doing this. In general, we just data mine, so we'll just look for what looks promising. So actually, even if we pick badly, when we do the sorting steps, basically you run the classifier, you'll drive an area under the curve, and then you kick out any metrics which are bad. We've got a few different approaches. We actually just had, no, actually it's not been published yet. We're developing a tool actually with David, who's a Beckman fellow, who we're developing ways to basically interactively look at the spectrum and see in a more sort of intelligent fashion what flags for different cell types. Or so that's more, up until now it's been more just sort of like, it's been very laborious going and looking for potential metrics. But there are more intelligent ways to do that. One thing you can also do is do things like principal component analysis, drive a loadings plot. That'll tell you where the variance is, or even a linear discriminant analysis, and then use that to sort of guide the metrics. Yes. Yeah, we haven't done too much PLS. Raman we do quite a bit. Actually, I think Matt probably spoke about it last week with PLS. But yeah, PLS is a good way as well. Yep. We're still at the point where it's preclinical. I work a lot with pathology in Chicago. They're very excited about this. I work with pretty much the whole department, actually. I work with about 7 pathologists up there. So yeah, I go to USCAT, which is the largest academic pathology conference in People are very, very interested actually in this. In fact, on Friday, something I chopped out at the last moment, we can also replicate staining. Actually, on Friday in the post session, I have a post which I show that. I should have put in this really. And we can basically replicate staining very accurately for H&E or UIUC stains. But it's a good question. It's a lot of this work, so my next step is really to work with pathology to figure out what do they want and in what format. It's all good and well doing this, but if they're like, this isn't useful or I can't use this is why things like the Bayesian are useful, because it basically removes the spectroscopy element. I have so many conversations where they get RAM and mix it with IR, so it has to basically remove any spectroscopy element. It has to be an image at the end of the day, I think is the right way to do it. But yeah, I think my feeling on this at the moment is that you're not necessarily going to replace staining, certainly in the near future. The pathologists I work with, they typically want this, they're really excited about this more for helping them with things that current methods fail on. I literally have a pile of projects where they're like, sarcomas, for example. It's very difficult to tell the cell type of origin with sarcomas. There just aren't the stains available. Types of lymphoma, thyroid cancer. So this type of thing is very, very useful for that, where they simply don't have approaches to do that now. So I think that's where the niche is, with both IR and random. Cool, I better wrap up. We're at 10 o'clock. What happens now? Do you go for coffee or do we start the next person?
I think it's coffee break.
Okay.